Welcome to the first video in our comprehensive course on quantum field theory. In this video, we will take our first steps into one of the most challenging and fascinating areas of modern physics. In quantum field theory, the mathematical challenges can be intense. Expect to encounter complex calculus, advanced algebra, and intricate concepts from linear algebra and differential equations. But don't worry, in this course we break down these complexities into manageable steps. This first video is designed to ease you into the mathematics behind quantum field theory gradually, introducing foundational techniques and explaining them in a straightforward way. My name is Shaunak and you're watching this video on my channel Physics for Students. Welcome to the first video on learning quantum field theory. Well, first we need to know on a basic level as well as going a little bit deep that what is quantum field theory. Now, in general in theoretical physics, quantum field theory is basically a theoretical framework which combines three pillars of physics: classical field theory, special relativity, and modern quantum mechanics. So as you can see, it includes three theories: classical field theory. I have mentioned the name of Isaac Newton and James Clerk Maxwell in general to combine the classical field theories of gravity and electromagnetism. Then comes Einstein's special theory of relativity 1905, which changed our entire perception of space and time, and quantum mechanics generally introduced by Max Planck, which led to the quantization of energy and so on. So classical field theory, special relativity plus quantum mechanics equals to quantum field theory. And in classical field theory, what I'm trying to mean is that Newton's laws of gravitation and Maxwell's electromagnetism. Now, this is overall a definition, a kind of an understanding of quantum field theory. So from this first definition, what becomes clear is that the mathematical complexities which will come forward are because it is actually combining three concepts of physics. So one will be classical mechanics, then you will get equations of special relativity as well as quantum mechanics. So obviously if you're combining three equations into one single, then obviously the equation will be big and complex. Now from this quantum field theory definition, we get three important aspects. One is that this actually provides a unified description except gravity, because we are still searching for graviton, or string theory has not itself proved. So it is the gravity is excluded. But other than that, all of the part of the fundamental forces are included. The second thing which comes are technological advancement, because as you see in the recent researches also, quantum field theory are actually including and developing lot of technological advancements, including quantum cryptocurrency, quantum computing, and a lot of other quantum phenomena. So yes, technological advancements are there, and there are a lot of interdisciplinary actions. That means quantum field theory is not a standalone theory, but it is taking into condensed matter physics, superconductivity, and quantum Hall effect. So these are actually the three parts. It provides a unified description. It is still helping mankind into technological advancement, and it is including a lot of interdisciplinary applications, including condensed matter physics and others. Now, in order to get a better deep idea of quantum field theory, what I would do is that I will give you certain ideas. First is that we know that those who have, obviously if you're doing QFT, you already know quantum mechanics. Their particles are treated as objects. I'm to say there are objects like electron or a neutron, etc., and they have got different complexities mathematical. So they are treated as point-like objects. Now, when we come to quantum field theory, these are not anymore objects, but what they are something kind of an abstract concept which is called a field. That is why it is called field theory, and that is called quantum mechanics. Mechanics itself, the word comes from Newtonian mechanics, where we consider the concept as point-like particles. This is one of the most fundamental difference. Now here you see that in the classical world we think particle as tiny localized object. That means it has got a momentum, it has got a position, it has got a gravity or whatsoever. It has got something which are very localized, and we are trying to define in mathematics or intuitively understand that localized behavior. On the other hand, if you consider the particles in kind of a Bohr's model or the typical quantum mechanics, you will see there's a nucleus, there's a proton and electron somehow going around it or so. But here, it is both the particles behave like wave behave like particle, so we call it a wave-particle duality. This is as part of quantum mechanics is considered. So properties of particles such as energy and momentum are quantized, and you know that comes from quantum mechanics, that it cannot have a continuous flow and an infinite amount of energy, but it is discrete and quantized. So this one, which is called the probability amplitude or psi, whatsoever you call it, this describes the probability of a particular particle's quantum state. Remember, it only describes the probability. We cannot know for certain where the particle is, just a probability regarding its function, position, momentum, spin, and so on. So this is another aspect of what we are going to learn in quantum field theory. So particles, as you can see, are now fields. And fields are basically a kind of a mathematical abstract understanding that permeates all space-time. So you cannot pinpoint now and say that here is an electron or this is a particle, but it is all spread over. It is all spread over space and time. So here you can see this is a kind of animation which I have taken from the internet, and this actually shows that the fields are spread throughout, and they are continuously varying, and their excitation at every point. Now you see the entire scenario from classical Newtonian mechanics, classical non-relativistic quantum mechanics, how we are emerging into fields. So if I draw this one, this is a space, and this space, each and every point in the space is being quantized. Or we say that there is a mathematical object that assigns a value to every point in space and time. Now you might argue with me that, okay, this space and time, this quantization is also done in quantum mechanics. You are absolutely right. But that quantization is based on certain things which quantum mechanics says, but here we will come to certain things which are called operators. So the position and the momentum, what we define in terms of Lagrangian and Hamiltonian, will now change. So till now, this is what is quantum field theory. This is something which is an assimilation of three theories. It is definitely giving up a lot of advancement in technology, and these are where the particles are not behaving like particles, no localized description, but it is an abstract object that permeates all the space and time, and the mathematics is to assign value for every point in time and space. Now from here, once we understand the quantum field theory, or what is quantum field theory, there are certain approaches to understand quantum field theory. Now, as in classical mechanics also, you learn with two different approaches, calculus or simple understanding. In quantum field theory also, there are two approaches. And in order to know those approaches are very important, because depending on the approach, the mathematics and the concepts vary. So if I take quantum field theory as as a whole, it provides the framework to understand particles and their interactions. Then the first approach is called canonical quantization approach. So I will define what it is. So let us understand that to construct and analyze quantum fields, the physicists developed two different approaches. One is the canonical quantization approach, and the second one is called the path integral approach, or some people call it as sum over histories approach. Now, in the word canonical is actually meaning according to, ordered by canon law, or you can say it is related to a rule established by the parish or the church. In general, from the literary meaning, we try to get a kind of an understanding of what the subject is. So canonical means that it is by order, a kind of a strict order, and this strict order emerges from something which is well established, which is called classical mechanics. So and path integral approach is something which was developed by Richard P. Feynman. So, and this approach actually uses the sum over of all histories or all paths of a system in order to compute the probabilities. Now, in case of what we call a canonical quantization, so the question now is that why there are two approaches. But before coming to that, I would like to tell you that canonical quantization actually starts with classical field theories, just as it starts by the church's law or by the Christian rule. So here also it starts with classical field theories, and it promotes the fields, their conjugate momenta, to operators that satisfy certain commutation rules. And a path integral approach is something which is using the concept of summing over all possible histories of paths. That means this one, and compute probabilities to other physical qualities. So these are the two, although there are many other approaches, but primarily there are these two approaches. The question is that why there are two approaches? Why don't we have just a single approach and go ahead with that? Obviously, there should be some reason for a kind of two approaches. Now, in order to understand that, if you go by the origin of how we started understanding physics or mechanics, is basically started with Newton's Principia Mathematica, which he described force of gravity as action at a distance. Then came what is called electricity and magnetism, which was the term field was itself coined by Michael Faraday. And then came the entire 4 or 8, 20 equations of Maxwell's, which united electricity and magnetism. So Newton's Principia Mathematica along with Maxwell's equation were going very well for centuries. But after that, what we found is that there is some kind of a theory which breaks down, which is called black body radiation. If you want to know more, you can go to my new series on lectures on quantum mechanics, the course where I have actually mentioned. So there is an ultraviolet catastrophe, energy level going so high that the general physics law are breaking. So Max Planck found to the equation E equals to h nu, which means energy is equal or proportional to the frequency. Along with that, there is a constant, and photoelectric effect developed by Albert Einstein showed that the energy is basically quantized. Now, from here, if you look into the development, how we started with Principia Mathematica and went to photoelectric effect, what we find is this. So canonical quantization is basically a method for quantizing classical theories, especially fields, by extending the principles of quantum mechanics to systems described by classical mechanics. So it is originally applied to the systems of finite degrees of freedom. So canonical quantization was later adapted to infinite degrees of freedom. So what we get from here is that automatically it comes from the historical development. So the question is that why it has got two approaches. First is that obviously we start with the classical and then move into the more complex things. So we get the classical physics, we extend it to quantum mechanics, and from quantum mechanics, when we get the quantization, we go into quantum field theory. Very simple. So this is the reason. History shows us the path. History gives us those incumbents that we have to develop a new theory. Now, also there is something which is called clear physical interpretation. What do I mean by that is that this quantum field theory treats time and space asymmetrical. That means it is not symmetrical, which will be in quantum field theory, which we see, as it relies on what is called time and space, and it relies on the Hamiltonian that evolves the system over time, just in case of a Schrödinger equation. This can be challenging on relativistic theories where space and time should be treated equally. The next thing, so this can be a concept simpler compared to the path integral of Feynman, which we will see later. Another important thing is that the extension of quantum mechanics. So in case of a quantum mechanics, it extends, for example, a classical field that describes physical quantity, for example, electricity or magnetism. This formulates the system using Hamiltonian, where the field gets extended. So we have got a field operator, and then we have got a conjugate momentum operator. So the first one is that canonical quantization is giving us what is called a simpler understanding rather than path integral, because our brain is wired to imagine space as time to be different. Also, it extends the quantization of classical mechanics to field theory, and it promotes the general fields which we see in quantum mechanics into conjugate momenta operators. So that again becomes extremely important. The next part is called this one, creation and annihilation operator. Now, in general, in quantum mechanics, creation and annihilator operators are tools to describe quantum states. So canonical quantization, what it does is that it involves defining and working with creation and annihilation operators, leading to directly to concept like particles and their interaction. So if I take this kind of an equation, you see that annihilation operator A reduces the number of particles or quanta in a given state by 1, this one. So it reduces the number of particles of state by 1. When applied to the quantum state n with a quanta, it lowers the numbers of quanta, and it is given by this equation. So that is why it is n minus 1. So this is a very important aspect, that the creation and annihilation operators are also taken care in case of a quantum field theory. The next path, what we come, is called the path integral approach. So we are done with this part. If you go back, so this page actually gives you what canonical quantization offers. Clear physical interpretation is an extension of quantum mechanics, and also it helps to understand creation and annihilation operators. Now, contrary to this, if you go into the path integral approach or the sum over histories, it actually calculates the probability amplitude of a particle's movement from one point to another, but it does not take one. It takes all the possible path that particle could take. It takes every single path. So the central concept is the sum over paths, which mathematically represents the probability amplitude for a particle to move from one point to another. So if I take this kind of an equation, fundamental equation of path integral approach in quantum mechanics, here you can see this K. This K is what? This K is the propagator, and it encapsulates all possible paths, each weighted by a phase factor exponential to I h bar s. And this integral operator, this is actually representing what? This is representing the sum over all the possible paths from xi to xf. I mean to say any point, the interval that we are taking. So it takes from xi to xf. So here there are 2 points. So instead of going from this to this and this to this, we are taking this one. We are taking all the blue lines. Here you can see all those blue lines which are emerging. So from here, what we get very importantly is that the propagator, which we see K, although we will deal with path integral approach later as it's just an introductory video, represents probability amplitude for a particle from an initial position x at time t, x, there is x and there is a time t, to a final position xf and tf. That means final x position and final t position. And the integration dxt represents that it is summing over all the paths. And the propagator encapsulates all the possible paths. So from here, what we can understand is this, that canonical quantization provides a natural extension of quantum mechanics, operator-based methods, and insights into quantum states. And path integral approach is little bit abstract, but it takes over all the different paths, etc. So what sets path integral approach apart is the ability to capture a full range of possibilities for a particle trajectory. So uniqueness of the path integral approach is that captures all the range of possibilities in a way that integrates all of quantum mechanics probabilistic behavior. And most importantly, each path is assigned to a complex exponential weight proportional to this action S and this one, that which I was talking about. This is the complex exponential weight proportional, and you know h bar is the reduced Planck's constant. So what it does is that this allows for contribution for even non-classical paths and captures the interference patterns which are very crucial to understand quantum phenomena. Here is the summary. It also allows non-classical paths, so the interference phenomena, which is very crucial, is also taken into account. The next thing that we get in path integral approach is that it handles many degrees of freedom. So that means it provides a very, very natural way in which it can handle even with infinite number of degrees of freedom. And this becomes very important in terms of understanding of particle physics. Because in case of particle physics, how particles interact, how they provide different degrees of freedom, all of these things are there. And lastly, but the most important, is the action principle. And action principle is central to the path integral, which encodes the entire dynamics of the system. As you can see, the L is the Lagrangian. So instead of a single path, it is taking all the possible paths, and it actually encodes the dynamics of the system. The contribution from all paths reflect the effect of the action and therefore of the underlying physical laws. So if you consider path integrals, they do not rely on operator formalism, which you have seen in canonical quantization. So the focus is integrating all possible paths weighted by this one, the complex exponential, and this approach does not require explicitly defining position and momentum operators, which was required in the classical quantum mechanics or the canonical quantization. So that is why there are two approaches. Two approaches have got two advantages, two complexities, etc., two different complexities, and it helps us to understand. So as I was telling that yes, there is a quantum interference which is taken care, because when the path integral incorporates the quantum interference, so hence it gives the complete full range of possibilities. So here you can see all those lines from point A to point B. So that is why it is very important. Now, if I take canonical quantization approach on the left hand side and path integral approach on the right hand side, so first what we get is that fields are treated similar to particles. Second is what we get in the path integral approach. This formula approach reformulates quantum mechanics in summing over the paths. Here, useful in understanding the particle interpretation of quantum field theory, and it maintains a clear picture of time and space as it takes it asymmetric, and the time evolves over the Hamiltonian just like Schrodinger equation. It gives a more probabilistic picture of how fields evolve. So from here, what we get to understand is that canonical quantization approach is much more easier to understand. So why it is much more easier to understand? These are the reasons. It is much more intuitive because canonical quantization directly promotes classical variables like position and momentum, which we are quite aware about. Operator algebra, the mathematical framework of operator algebra, is well established and it is widely used in quantum mechanics. Also, it involves conceptual simplicity and the time evolution, because canonical quantization leads to Schrodinger equation, which governs the time evolution of quantum states, and this is often easier compared to Feynman's path integral formalism. So this gives you an approach that why there are two approaches, what are the two approaches, which one serves what purpose, and how they evolve. Now we are constantly talking of quantizing and quantum field theory. We come to the next part of our video where I would like to explain that what is quantization. This is central to our understanding of quantum field theory. Now, when we talk of quantization, quantization is basically a process that converts the classical systems, as mentioned here by the pendulum diagram, like those governed by Newtonian mechanics, where observables like energy, position and momentum take on discrete rather than continuous values. Yes, in classical physics, variables can vary continuously, but in quantum physics, certain quantities become quantized, meaning that they can take only specific allowed values. Now, as you can see that EXP, I mean to say energy, position and momentum, they can have continuous values and they can go up to infinity. And that was the reason that ultraviolet catastrophe happened. And that led to a new formulation by Max Planck, E equals to h nu. So that is what is called quantization. That means that we are we are converting the classical system into quantum system where they won't have a long range continuous values rather than discrete values. Now there is something which is called a first and a second quantization, which I will come to that later. Now let us take an example of this quantization in discrete vibration modes. For example, if you take this kind of a spring, it is a vibrating spring and it fixed at both ends has specific frequencies which are called normal modes. So the vibrations occur in discrete platforms based on boundary conditions, and these boundary conditions can resemble quantized energy levels which are seen in general quantum mechanics. Just an analogy. The next thing that we see is this one. Classical physics is often described by what is called the principle of least action, which is S integral of L dt, an integral of the Lagrangian over time. This is minimized, and in quantum mechanics this action becomes defining the path integrals, which leads to quantum behavior. Also, you will see that classical variables, as you see here, position and momentum, are converted into operators, and they follow this kind of a commutation. And this transforms classical equations of motion into quantum operators, which lays the foundation of quantum mechanics or quantum field theory in future. So what we see that what is quantization is converting classical systems so that they have discrete values. Now, in quantum field theory, we apply quantization to fields like electromagnetic fields. So if this is an electromagnetic field and these arrows, they point values at each point in space, and they become what are called operators than simple variables, and they can only commute relations similar to position or momentums in quantum mechanics. So this is another aspect. Also, you see here particles become no more particles, but these particles become excitation, field excitations. That means that particles, as seen by quantized excitation for this, in photon it is a quantized excitation of the electromagnetic fields, and QFT treats particles as quanta of the fields. So interaction between particles, so there will be different particles, again fields. There will be an electron field, there will be a photon field, there will be a meson field. So we will have different type of fields, because particles are no more particles, they are excitation in case of fields. So here we come to the conclusion that quantization actually helps us in moving from classical understanding where particles follow definite trajectories to a quantum perspective, which are represented by wave function, and their interactions are described by fields that propagate in space and time. So this is what is called quantization. So the next question obviously that crops up in your mind is that why do we at all need a quantization? I mean to say, is there at all a necessity, or we are just doing quantization for the sake of doing? Definitely there is a reason. Now this one which I highlighted in box, this ultraviolet catastrophe, which was the failure of the Rayleigh-Jeans law, this Planck proposed a new kind of a formula, E equals to h nu. So what happens is that the energy is quantized in discrete brackets, which classical theorists cannot explain. So because classical theorists cannot explain, we need quantization. Also, here you can see that particles at quantum scale, we know that exhibit both wave-like and particle-like properties. And quantization introduce a kind of a probabilistic description which can handle this duality. Otherwise, without that, classical physics cannot accommodate this idea that there is a wave-like as well as particle-like behavior. So how do we do that? And the next thing is that, for example, if this is x and y axis and the energy level, it goes up and up and up and up. As you see, this arrow is still going up and leads to infinity. This is not possible. We need quantization, because if radiation or energy can go up to instabilities, how do we make a theoretical framework? The typical Bohr's model, which we call the Bohr's planetary model, where the electrons keep on spiraling around a positive nucleus. So it should collapse. It should, go and the entire atom would collapse. But no, we came to know that there are discrete levels. The jumps happen in discrete levels. So all this actually leads to the conclusion that quantization provides actually the stability. It preserves the symmetry, most importantly, preventing the collapse. Now, in this case, for example, if in classical mechanics, if we take a harmonic oscillator, we know that it in general can take energy value, any energy value. But remember, in quantum mechanics, quantizing the system is done by using the Schrödinger equation, where this H Hamiltonian is equal to this, and this gives a lot of discrete eigenvalues. And these discrete eigenvalues are actually the quantized energy spectrum. And they actually behaves like the stability of atom structures, where electrons occupy discrete energy levels. So from here, what we can see is that we go to the same electromagnetic field, and what we are trying to do is that in quantum field theory, we are taking this electromagnetic field and quantizing them similarly to particles. The field itself is treated as an operator that can create or annihilate particles. Remember, this field is taking as an operator which shows the creation and annihilation of particles. So if we consider, so we take fields and we similarly draw as a particle. So if we consider a scalar field, for example, phi of x, you can take it also phi of x comma t. I have ignored the time. The classical Lagrangian actually expressed like this. This is the classical Lagrangian. Now, what happens in quantum field theory if we promote this phi x to this phi hat x? That means it becomes a field operator. And if we decompose this, this is the term which shows the creation and annihilation operator. And what you see, there are two important terms, A sub k, and it has got a dagger. So these operators actually shows the creation and annihilation of particles, and allowing us to describe particle interaction as excitations of the underlying field. So the quantization of the field implies that the number of particles is not fixed. Here it comes. This is a very important part. The number of particles is not fixed, unlike in quantum mechanics, which is fixed. And this enables us to describe phenomena like particle creation and annihilation. Now, what do I mean by the number of particles is not fixed in quantum field theory, which I would like to show in the next part of the video. Now, in quantum mechanics, we often deal with system which has got a fixed number of particles. For example, in a hydrogen atom, we consider one electron bound to one proton. This animation shows you that a system of interacting electrons, like an atom or molecule, the number of electron is also constant. And in such system, how do we define this system? In terms of particles wave functions and the Hamiltonian, the energy operator. So it is either a psi or an h hat, which is the energy operator, which reflects interaction between fixed set of particles. Now, in terms of quantum field theory, what happens is that these becomes fields. So fields are the fundamental entities rather than individual particles. So what happens is that we get a kind of a field excitation, and this field can oscillate and propagate without any quantization in case of electromagnetic field. But here you can see that we get an electric field, then a photon field, and so on. So we say that in quantum field theory, we quantize the electromagnetic field, which means that we promote it. We put it up, we give a promotion it to an operator that can create or annihilate a photon. So in classical electrodynamics, the field can oscillate and propagate without any quantization, which means it can have any value. Again, it is leading to catastrophe. In quantum field theory, we quantize the electromagnetic fields, which means we promote it to an operator that can create or annihilate operators. So let me give you an example. For example, in quantum field theory, this electron actually can produce another photon. For example, in QFT, the number of particles is not fixed because of this. Now, this photon can again, due to high energy photon interaction, can actually produce an electron. This photon can produce an electron. And then again it can produce a positron pair, and in this process the number of particles changes from one photon to one electron to one positron. So here you can see the number of particles are absolutely not fixed. So in quantum field theory, that is why I have just told that in quantum field theory number of particles are not fixed, because it starts with one photon but it gives one electron and one positron. So in this case, we actually create what we say that a dagger, which I was saying that it creates particle, and also this annihilate particles. The creation operator adds the particle to the system, and the annihilation operator removes the particle from the system. So here comes the last few important, I would say, summary that we need to remember. One is that in quantum field theory, remember, particles are not fundamental entities. They are just excitations of the underlying quantum fields. These fields actually permeate all of space-time and can be excited in various ways. Each excitation corresponds to a particle and the number of excitations it can exchange. And most importantly, operators in quantum field theory can increase and decrease given the number of state of the particles. So it is again not fixed. So quantum field theory allows the creation and alienation of particles. Operators in quantum field theory can increase and decrease, and this is in stark contrast to quantum mechanics, where we have seen how the particles of a system are absolutely fixed. So that brings to our end to today's video. This is the first video, and we learned about what is quantum field theory, what is quantization, why do we need quantization, the two different approaches, the canonical approach and Feynman's path integral approach. So that's all for today's video. I would like to thank immensely for those who have taken up time to watch it. Please do subscribe to my channel Physics for Students and click on the bell icon to get all the notification from Physics for Students. You can write to this ID, and I have already started giving new videos to my new channel General Theory of General Relativity Explained, and you can follow me on my Facebook, LinkedIn, Instagram and Twitter account. So this is the first video, and we will continue in a complete course of learning quantum field theory step by step. We'll see you soon in the next video, but till then, goodbye.